High-strength steel fails under 1 to 2 gigapascals of tensile stress, but a single carbon nanotube can withstand up to 100 gigapascals before breaking. If engineers can replace structural steel with a material that strong, reducing component mass by 70%, the limits of electric vehicle range would extend significantly. However, engineers do not forge entire car frames out of pure nanotubes. They are used far more strategically in modern manufacturing. Instead, they serve as a microscopic reinforcement scaffold infused directly into a polymer matrix, such as an epoxy resin. Building a vehicle with these properties requires manipulating load-bearing structures at the atomic level. For over a century, safety and capability improvements meant adding physical weight. Every new safety cage, larger engine, and complex electronic system requires more material, usually heavy steel. That mass is the enemy of kinetic efficiency. Moving a heavier object requires more energy to accelerate and demands more mechanical force to stop. In electric vehicles, this becomes a compounding problem. Every extra pound of chassis demands more output from the battery, shortening the total driving range. Current attempts to substitute steel with aluminum or traditional carbon fiber have reached a limit, either sacrificing structural integrity or remaining too expensive for mass-market production lines. Achieving radical efficiency gains now requires a completely new structural approach to how a modern vehicle is built. The mechanics of this new approach start with graphene, a flat, two-dimensional sheet of carbon atoms linked in a hexagonal lattice. When this sheet rolls into a perfect cylinder, it becomes a carbon nanotube. This data visualization charts the tensile limit of that single nanotube. Because it relies on carbon bonds, it can withstand up to 100 gigapascals of force. Compare that directly to the secondary bar representing high-strength automotive steel. The steel tops out between 1 and 2 gigapascals, a 50 to 100-fold difference in capacity. It achieves this while maintaining a density approximately 1/6 that of steel. This extreme strength-to-weight ratio is possible because the structure bears loads through atomic geometry rather than the sheer bulk of the material. To produce these structures at an industrial scale, manufacturers use chemical vapor deposition. A carbon-rich gas reacts in a furnace, causing nanotubes to physically grow upward. These raw nanotubes are harvested and mixed directly into a liquid polymer, forming a composite matrix. In standard carbon fiber parts, the thick, macroscopic carbon strands act like steel rebar in concrete, providing the primary rigid structure. This diagram shows how carbon nanotubes fit into that hierarchy. Making up less than 1% of the total component weight, they form a microscopic mesh within the resin itself. When physical stress hits the part, this underlying network distributes the force evenly across the entire matrix. It physically arrests microscopic cracks before they can spread and cause a complete component failure. These nanotubes provide their greatest utility by fortifying the surrounding matrix, preventing structural failure at the microscopic level before the entire part is compromised. This wireframe CAD model isolates a vehicle door to illustrate the 70% mass reduction claim. That drop applies specifically when replacing a single steel component with a nanotube composite equivalent. Replacing that single panel triggers a systemic domino effect known as secondary weight reduction. When the primary body shell weighs less, engineers can downscale the mass of the powertrain, the suspension coils, and the brake assemblies. The math behind this cascade is clear. Every 10% reduction in total vehicle mass yields a 5 to 10% improvement in overall fuel efficiency. Removing structural mass at the component level produces a multiplier effect, increasing the efficiency of the entire machine. Because nanotubes are composed entirely of carbon atoms, infusing them transforms an otherwise passive polymer resin into an electrically conductive network. This allows the chassis itself to function as a built-in sensor grid, using changes in electrical resistance to detect material fatigue and alert the driver to hidden structural damage. Mechanically, the nanostructure absorbs and disperses severe impact forces far more effectively than steel, while remaining immune to rust and corrosion. Inside the powertrain, battery manufacturers are applying these conductive properties to electrodes. The nanotubes facilitate faster electron transfer for rapid charging and improve thermal dissipation. CNT composites transform the chassis into an active, multifunctional subsystem critical to the car's electronic and safety infrastructure. Right now, high manufacturing costs and the difficulty of scaling extreme precision chemical vapor deposition prevent immediate full chassis rollouts. Instead, the technology is entering production through smaller applications, such as conductive additives for electrostatic paints and reinforcements for high-performance tires. Dedicated electric vehicle manufacturers like Tesla are actively testing these composite infrastructures to extract every possible mile of battery range out of a lighter frame. Legacy automakers like BMW are also expanding their carbon composite production lines, establishing the industrial capacity needed to scale these new materials. In the aerospace sector, NASA is testing nanotube composites to replace structural aluminum on spacecraft, aiming for a 50%. This automotive shift is happening component by component as material costs continue to drop. Manipulating the physical bonds of a single carbon atom at the microscopic scale is rewriting the engineering limits of the modern vehicle. To explore more of the systemic engineering frameworks reshaping the industrial world, subscribe to the channel.